is geosynchronous satellite launch vehicle, or in short as we know as GSLV. Now when it comes to GSLV, this is the next kind of operational launch vehicle, and this is where we can launch heavier satellites as well. So when we discuss all the variants of PSLV, we see that all these variants cannot launch a very heavy satellite. For example, the heaviest variant that we have for PSLV, the PSLV XL variant, it has a maximum capacity of 1425 kg to geosynchronous transfer orbit, or GTO. So a communication satellite which is heavy, you'll see that any communication satellite is at least 1800 to 2000 kg. It can be 4000 to up to even 6000, 7000 kgs in weight. So in that case, a PSLV cannot be used to launch this satellite. So in all these cases, we see that we need another kind of launch vehicle, and this is where GSLV comes into the picture. GSLV will be used to launch satellites which are going into the equatorial orbit, going into the GSO or GEO, that is geosynchronous orbit or geostationary orbit. So for that, we have developed this. Now, when it comes to GSLV, building GSLV has not been easy for India. If you look at the history of GSLV, the first operational launch that we did for GSLV was 2001. So until 2001, we did not have the capacity to launch a satellite which is heavy. So all the INSAT satellites, for example, most of these satellites were being launched with the help of France, or some, in case of some, with the help of Russia. So Russia and France were two countries which were helping us in launching all the satellites which were very heavy, the satellites which are communication satellites. Now, since 2001, we started to launch our own satellites, but you'll see that the success rate of the GSLV has not been great. The success of GSLV has not been anything as compared to what we have seen for PSLV. For example, for PSLV, we have seen that out of 50, 55 odd launches, there have been hardly 3 or 4 which have failed. But if you discuss about GSLV, in case of GSLV, we have seen that there have been 13 launches of GSLV Mark 1 and Mark 2, and there have been 4 launches of GSLV Mark 3. So out of the 13 launches of GSLV Mark 1 and Mark 2, and 4 launches of GSLV Mark 3, there have been at least 4 launches which have been unsuccessful. Most of them have been in case of GSLV Mark 1 and Mark 2, where we have seen a lot of failures. So the success rate of GSLV is approximately 75%, and when it compares to for PSLV, it is approximately more than 90 to 95%. So that's why GSLV, although has not been very successful, GSLV has not been very stable. But past few years, if you see everything, all the launches that have happened between 2014 to 2020, you will see that the launches now have been successful. The failures have not happened in the last couple of years, in the last 4-5 years. So that has been a big achievement for ISRO, that we have now been able to stabilize GSLV as well. What's the reason? Why have we seen that there have been so much of problem associated with GSLV? The main reason is the technology that is in use. When we talk about GSLV, GSLV has 3 stages. So in PSLV, we have 4 stages. The 4 stages being solid, liquid, solid, and liquid. In case of GSLV, we have 3 stages. The first stage still is the solid stage. The second stage is a liquid stage, and the third stage is a new kind of stage, which is a cryogenic stage. So here comes a new term, and this term is cryogenic. So let's try to understand what GSLV is. We'll look into all the variants of GSLV, and we'll understand what is cryogenic. So first of all, GSLV has 3 stages. The first stage again will be a solid stage. Then you have a liquid stage, and then you have a cryogenic stage. These are the 3 stages that you have here. Solid stage is still HTTP, the same as what we saw for PSLV. Same. Liquid stage also remains the same. You have UDMH here, which is being used in the liquid stage, and the third stage is cryogenic upper stage, which is something that we'll discuss separately. And then after that, you have the payload here. For example, we have taken the example of Chandrayaan-2, which was launched using GSLV. So this is where the satellite is, and these are the payload fairings, which are basically shielding the satellite which is kept inside. So in this, we have 3 variants. We have Mark 1, we have Mark 2, and we have Mark 3. So let's have a look at Mark 1, Mark 2, and Mark 3 and understand the differences between them. Now, as you can see on your screens, you have the 3 variants. Mark 1, MK stands for Mark 1, Mark 2, and Mark 3. Height for Mark 1 and Mark 2, 49.13 meters, same for both. In Mark 3, it is 43.43 meters. So in terms of height, Mark 1 and Mark 2 are longer as compared to Mark 3. Mark 3 is shorter than Mark 1 and Mark 2, even shorter as compared to PSLV. If you remember, we discussed about PSLV, all the variants of PSLV have the same height, that is 44.4 meters. Lift off mass, Mark 1 had 401 tons, Mark 2 415 tons, and with Mark 3 there is a significant improvement, which is 640 tons. Number of stages, in all the 3 cases you have 3 stages. First being solid, second liquid, and third being cryogenic. Payload to LEO, or payload to low Earth orbit, 5 tons, that is approximately 5000 kg can be carried. For Mark 2 also it remains the same, 5000 kg. With Mark 3 there is a significant improvement that we can carry up to 8000 kg in Mark 3. When it comes to GPO, or geosynchronous transfer orbit, Mark 1 can carry 2.5 tons, that is 2500 kg. Same for Mark 2, that is 2500 kg. For Mark 3, again you have a significant improvement that it can carry 4 tons of mass, that is 4000 kg of satellite can be carried with Mark 3. So that's why now we have increased our capacity. In comparison to, if you look at PSLV XL, we discussed that PSLV XL could carry a maximum of 1425 kg to GTO. So that's why this is a very significant improvement when it comes to GSLV Mark 3. So that's why Mark 3 has been a big improvement when it comes to Indian launch vehicles. Mark 3, that's why it is the heaviest of the launch vehicles that we have today, and there have been significant improvement in the way it can carry the satellites. Now let's try and understand what's the meaning of cryogenic fuel. We have been using this term cryogenic, right? The third stage of GSLV, whether Mark 1, Mark 2, or Mark 3, the third stage is cryogenic stage, which uses cryogenic fuel. So first of all, what is the meaning of cryogenic? Whenever you come across the term cryogenic, just understand one thing, that cryogenic means anything that is working at very low temperatures. Usually something that is working at a temperature which is even lesser than minus 150 degrees Celsius would be called as cryogenic technology. So in terms of fuel also, when you have fuel which is working at less than minus 150 degrees Celsius, in that case we tend to say that we are talking about cryogenic fuel. In case of the cryogenic fuels which are being used in the rockets or the launch vehicles, these are cryogenic fuels that usually are using a combination of liquid oxygen and liquid hydrogen. So for example, the third stage that we have, the third stage of GSLV is using a mixture of liquid oxygen and liquid hydrogen. Now you have to understand that liquid hydrogen and liquid oxygen will be achieved at very low temperatures. For example, the temperature where oxygen from gaseous state will change to liquid stage will be about minus 183 degrees Celsius. In case of hydrogen, it is even lesser than that. In case of hydrogen, it can be as low as minus 250 degrees Celsius, less than 253 degrees Celsius. So this is what we are talking about. We are talking about mixture of elements which are in their liquid stages, and this liquefaction can happen below a temperature as low as minus 183 degrees Celsius in case of oxygen, and less than minus 250 degrees Celsius in case of hydrogen. So this is something that we observe for cryogenic fuel that is being used in the third stage. Now, on the basis of cryogenic fuel that is being used, there is the difference between the three terms. You have Mark 1, Mark 2, and Mark 3. Mark 1 is where we were actually using a Russian engine. With Mark 2, we had an Indian engine, and with Mark 3, we had a better variant of Indian engine. All these three, the difference we are talking about, the difference is in terms of the cryogenics that were used here. The cryogenic fuel that is being used, this is what was different in all these three. So, for example, if we start with our discussion on GSLV Mark 1, initially the story would have been completely different. If you go back to the history of cryogenic technology, India might have received cryogenic technologies back in 1970s itself. Now, back in 1970s, there was one help that was required, and France had come to India to take that help from India. And India also helped France at that point of time. And when India helped France, in return, France had provided a copy of their liquid stage engine that was the Viking engine. The Viking engine which was being used by France. This same Viking engine, a version of this Viking engine became Vikas engine in India. So Vikas engine currently we are using for our liquid stage. The second stage and the fourth stages, they use Vikas engine. And this Vikas engine is used to carry the liquid fuel. It has been one of the most stable engines that we have seen. So this happened. Now, since India helped France, France was successful with everything here. France had another issue that they came across. And then they came back to India. And this is again, we are talking about 1970s, when France came back to India and asked for some help. This time, India refused. This time, India said that India already had too much on its plate. That is, ISRO was working on a lot of projects, and it was not possible for ISRO at that point of time to provide any kind of support, any kind of help to France. Now, at this point of time, it's very interesting for you to know that if India would have helped France at that point of time, France was ready to provide India with cryogenic technology. Now, you have to understand, cryogenic technology is not something that is available with everyone in the world. If you just count the number of countries that have cryogenic technology, there are hardly some countries. You have it in USA, you have it in France, China, Russia, and India is also one of the countries. So that's why in the world today, there are not many countries who have cryogenic technology. Even today, we are talking about back in 1970s. So in 1970s, India would have been provided with cryogenic technology, but some miscalculations on our part, and you can say possibly it was not something that India would have seen in the hindsight at that point of time. So at that point of time, India did not receive cryogenic technology because India could not help France with whatever they wanted. Now then in 1991, this time Russia was ready. Russia was ready to provide cryogenic technology to India. This again was disputed by USA. USA went to MTCR to dispute this exchange. The transfer of technology that was supposed to happen from Russia to India, a company named Glav Cosmos, which would have provided the technology to India. Glav Cosmos was not allowed to provide the technology to India because USA took Russia and India to MTCR. What is MTCR? I'm very sure you know. It was in use a couple of years back as well. MTCR is Missile Technology Control Regime. So under Missile Technology Control Regime, a country which is a part of MTCR is not allowed to provide any technology to a non-MTCR country. So Russia was a part of MTCR. USA was a part of MTCR. India was not a part of MTCR. And this we are talking about 1991 and 1992. So Russia, an MTCR country, was providing cryogenic technology to India, a non-MTCR country. Now, cryogenic technology is also something that can be used in missiles as well. It can be used in the launch vehicles. So that's why it was of the opinion that the same technology can be used for aircrafts also and for the missiles also. So that's why it comes under control of MTCR. It's not only something that comes under space technology. So Russia was ready to provide the technology. USA did not allow it to happen. It put sanctions on Russia, and then Russia had to back off. Russia could not provide the technology that we wanted. So this is when we started to work on our own technology. 1993, 94, mostly 94. It was when we started to work on cryogenic technology. We started to develop our own cryogenic technology in 1994. Then Russia was allowed to provide the engine. Russia did not provide the technology to us. Russia did provide the engine to us. This engine was known as KVD-1. This engine was KVD-1, and this was the cryogenic engine. This was the cryogenic engine that was provided by Russia to India. So in our first GSLV Mark 1, we were not using Indian technology. We were not using Indian engine, but rather we were using the Russian cryogenic engine for our third stage. The first and the second stages were ours only, but the third stage, the engine was being provided by Russia. And this was GSLV Mark 1. KVD-1 was the name of the engine, and there was a difference in the way this engine works. For example, it is something which is also called as stage cycle. The technology that is being used in KVD-1 engine was stage cycle. No need to know what was stage cycle, but just know that this has not been seen to be very stable. So that's why you'll see that there have been 7 launches that were tried with GSLV Mark 1 with this engine, and out of these 7, there were only 2 which were successful. Out of 7, only 2, 5 were failures. So that was a big concern for India. And meanwhile, anyway, India was working on its own cryogenic technology, and this is where we became successful after a while. And then this is where we had GSLV Mark 2. So GSLV Mark 2 is when we had our own cryogenic engine, which was called as CE 7.5. This was a new way in which the cryogenic technology was being used. This is called as gas generator cycle. Again, not required that you know what exactly is the meaning of gas generator cycle. Just know that there is a difference between the two. And gas generator cycle has been seen to be much more stable as compared to the stage cycle. So that's why you'll see that with Mark 2, the success rate also increased. There have been hardly a couple of failures that happened with Mark 2. So we became much more stable. Problem was, still this engine was not good enough to carry large amount of payloads. The thrust that is being provided by this particular engine was not that great. Then we improved upon it. And this is where we come to GSLV Mark 3. And this GSLV Mark 3 is using an engine which is called as larger amount of thrust. And that's why we say that now we come to something which is of the international standard. With GSLV Mark 3, with this variation of engine that we have now for cryogenic technology, this is something that is said to be of international standard. And this is where we have improved a lot. And with Mark 3, with this particular engine, we have not seen any failure yet. It took a lot of time for us to develop. For example, we wanted to be ready by 2014, but ultimately by 2017 we were ready, and we have not seen any failure as such with GSLV Mark 3 yet. So GSLV Mark III is a big achievement for India. And that's why many a times it is said that GSLV Mark III should not even be considered as a variant of Mark I and Mark II. GSLV Mark I and Mark II should be seen separately, and GSLV Mark III should be seen as a different vehicle altogether. But the bottom line is that all these are the ones which are being used for heavier satellites. All these launch vehicles are used for communication satellites. So more or less, you can say that they are in the same bracket, right? So this is about Mark 1, Mark 2, and Mark 3. Now we come to another topic, that is Vikas engine. We just mentioned this Vikas engine. What is Vikas engine? This is the engine which is used for the liquid stages. It is used for the liquid stages that we have both in PSLV as well as in GSLV. Both for PSLV and GSLV, we are using Vikas engine liquid fuel compared to Viking engine. So we took the technology from them and we created a better variant of the same that is being used by France. So Vikas engine has been highly successful, very stable form, and is being used for the liquid stages. So just remember these few points about it. It is used in both PSLV and GSLV series of launch vehicles, and it can be used for the liquid stages as we discussed. So just remember a couple of points about Vikas engine. Nothing beyond this can be asked in the examination. Right. So let's move on. Now we come to the future of launch vehicles. We had discussed towards the beginning that historic launchers are SLV3 and ASLV. The operational launchers are sounding rockets, PSLV and GSLV. And we had discussed about the future launches where two names were discussed. One was scramjet and second was RLV or reusable launch vehicles. So now let's have a discussion on what is the meaning of scramjet. 2016, there was one successful attempt that was done by ISRO, and that was at a testing of scramjet engine. What is the meaning of scramjet? If you look at this term, you have basically two things here, SC and ramjet. Ramjet engines are normally called as air breathing engines. What's the meaning of air breathing engines? When we discussed all the launch vehicles like PSLV and GSLV, we discussed that there are fuels and they are carrying oxidizers with them. What happens is 70% of the mixture of fuel and oxidizer that you have is oxidizers. So what happens is that oxidizers have a huge weight in the entire setup. Now with ramjet, we say that it's an air breathing engine. Meaning what? It means that you are not going to carry oxidizers, but rather you are going to use the oxygen which is there in the atmosphere as oxidizer. So if we are able to do that, what happens now? What happens is that you reduce the total amount of oxidizers that are being carried. It means that the launch vehicle is lighter now. It means that more amount of payload can be carried. It means that the carrying capacity of the launch vehicle increases. So that's why scramjet as a technology becomes very, very important, because ramjet is air breathing engine. Any engine which can use oxygen from outside instead of carrying the oxidizer will be called as ramjet. SC stands for supersonic combustion. So when ramjet engine is working at supersonic speeds, at that point of time you will call it as scramjet. So that's why SC gets added to the ramjet setup. Ramjet engine is any engine that can use oxidizers from outside, that is oxygen from outside, and whenever it is working at supersonic speeds, it will be called as scramjet. So what happens is very simple. If you look at this picture that you have on your screen, first of all, this is where from the air comes in. This is the inlet, you can see. Now this air is being compressed, correct? When it reaches this point, this air has been compressed. And since this air has been compressed, what happens is now the temperature here starts to increase. Temperature will start to increase. At the same time, we'll see that there will be a fuel injector at this point, and fuel will be mixed with this oxygen. Fuel will be mixed with this oxygen at this point of the scramjet engine. So this is where the combustion starts, because this air already is at a very high temperature. Fuel has been mixed here, and that's where the fuel will start burning. And as soon as fuel starts burning, you will see that at this point of time, heat will be generated in the other part. A lot of heat will be generated, and from here on, you will see that the energy that was required, this energy will be obtained here. This energy will be obtained here, and that's why it will help in the forward motion of the engine or the vehicle altogether. So this is what happens, that there is an inlet of air which is coming in, and this inlet of air is being compressed. With compression, the temperature increases, fuel is mixed with this, and then oxidation of fuel happens, and the fuel will start to combust. And this combustion will produce the energy that is required for the forward motion of the vehicle. This is what happens in any ramjet engine, and if it is working at supersonic speeds, it is called as scramjet. So what is scramjet? Supersonic. What is the meaning of supersonic? One term that you are introduced to here is supersonic. What's the meaning of supersonic? Supersonic means that anything that has a speed more than the speed of sound. More than the speed of sound at normal temperature, normal pressure at sea level. Anything that is more than that will be called as supersonic. So here's one particular term that we use, which is called as Mach. So when we say Mach 1 or 1 Mach, we mean that this is speed of sound. Now, whenever you hear terms like 2 Mach, 3 Mach, 6 Mach, then it means that you have gone beyond the speed of sound. This is where you come to supersonic conditions. At the same time, if the speed is more than 5 Mach, then in that case, we tend to call this as hypersonic. So between 1 Mach to 5 Mach, we'll say that this is supersonic. When it goes beyond 5 Mach, we tend to call it as hypersonic. So these are the speeds. And whenever you come across terms like scramjet, you will come across terms like Mach as well. Even in terms of missiles, whenever a missile is tested, for example, a BrahMos missile being tested, you'll see that scramjet engine is being used there as well. So there also, since it moves at supersonic speed, you will hear terms like 2.8 Mach or 3 Mach, etc. So just understand what is the meaning of this term, Mach. So this is the future. I mean, instead of carrying the oxidizer, especially for the first two stages, which are inside the atmosphere. Of course, you cannot use this engine when you are beyond the atmosphere, where oxygen is either very thin or absent altogether. So in that case, of course, it cannot be used. But for the lower stages, the first and the second stages where the launch vehicle is inside the atmosphere of the Earth, this is where you can precisely use scramjet engine. This was successfully tested back in 2016. Then after that, we have another technology which is called as RLV. Again, something which was tested back in 2016. What is RLV? RLV stands for reusable launch vehicle. It stands for reusable launch vehicle. So this is a kind of launch vehicle that can be reused. Now, the concept on which it works is just similar to if you had a manned mission. A manned mission will have to bring back the astronauts which have gone with them. Of course, they cannot leave them there, right? So the technology that is used in all these missions, the same technology we are trying to ape here for RLV. Again, it was tested back in 2016. It was successfully tested, and ISRO is looking to make RLV a possibility in the upcoming launch vehicles. So again, something that can be used in the first and the second stages whenever you are inside the atmosphere. RLV is a technology which is already being used by some of the other agencies. For example, SpaceX back in 2019 already started using it in their operational launches. India right now has just done a successful trial, and we are making sure that in future RLV becomes a possibility for us as well. So this is a picture that was floated by ISRO when the experiment was done back in 2016. That this is where from it starts. This is called as the ascent phase. And then after that, we see that it moved forward. It went to the height that it was required to reach. And ultimately, the descent started to happen. And it fell to a place which was marked in the Bay of Bengal. The good thing was that there was a 100-meter radius that was defined for this fall. And the final fall that happened, it was very near to the center that was there, approximately just 10 kilometers away from the center. So that's why this was also very highly successful. And again, something that ISRO has been working on. This is reusable launch vehicle. So again, something to be considered in the future. So from the future perspective, these are the two things that have been planned by ISRO. Now, after that, we have discussed about different kinds of fuels. So just quickly to summarize the different kinds of fuels that I spoke of. First, HTPB. What is HTPB? The solid fuel. The solid fuel which is being used in the first stage and the third stages of PSLV and in the first stage of GSLV. So hydroxyl terminated polybutadiene, solid rocket propellant. After that, we have UDMH or unsymmetrical dimethyl hydrazine. This is a liquid propellant, something which is being used in the second stage, both in case of PSLV as well as GSLV. Then comes MMH, which is monomethyl hydrazine, again something which is being used in the fourth stage in PSLV, not used at all in GSLV. So these are the three fuels that are being widely used. Apart from that, you have LOX and you have LH, that is liquid oxygen and liquid hydrogen. A combination is being used in the cryogenic engine in the third stage in GSLV. Then after that, you have MON. MON basically stands for mixed oxides of nitrogen. So this contains nitric oxide, dinitrogen tetroxide, or nitrogen dioxide. All these possibilities are there. So it can be NO, it can be NO2, it can be N2O4, it can be N2O. The mixture of all these different oxides of nitrogen are being used in the mixture of oxides of nitrogen. So these are the oxidizers and the fuels. Apart from that, one more that you can add to the list is PVC, or something that stands for polyvinyl chloride. Again, this is a solid fuel which is being used in the sounding rockets. So these are the fuels that are being used by ISRO. So just understand the basics about them. Nothing beyond this is required for the examination.